Greetings, fellow mathematicians. We're going to take a look at our fourth example using the method of undetermined coefficients, but this one is a lot more complicated than the previous three. We're going to get started, as always, by first finding the complementary solution. So we solve the differential equation where the right-hand side is 0. That's the homogeneous ODE. And we're going to convert to the characteristic equation, but be careful. Your y or function term does not give you a factor of r. Only the derivative and second derivative terms give you a factor of r or r squared, respectively. So convert carefully. The correct characteristic equation you get is r squared plus 9, not 9r, equals 0. And we can solve that very quickly. Subtract 9. And then take a square root. And we get imaginary values. I always like to write this in the form of a complex number, where the real part is 0, and the imaginary part is 3. So we can identify the real part, a, which is 0, the imaginary part, b, which is 3, and we just need to plug these values into the general solution in this case, where we have e to the ax terms times sine and cosine of bx, but if a is 0, e to the ax is 1, giving you just sines and cosines. So your complementary solution looks like c1 times sine of bx, and then a similar cosine term, c2 times cosine of 3x. That takes care of the complementary solution. So we can move on now to looking for a particular solution. To do that with the method of undetermined coefficients, we look at the right-hand side, what we've been calling g of x, which is x times sine of 2x. And that, we want to look at it as a degree 1 polynomial times a sine function. So our choice for the particular solution will look like a general degree 1 polynomial, ax plus b, times sine of 2x. And anytime you have just a sine or just a cosine, you always need to include the other in your form of the particular solution. So we're going to get another degree 1 polynomial, but now with two more coefficients, cx plus d, and that is multiplying cosine of 2x. Now for this example, almost all of the work is in calculating the first and second derivative of the particular solution, so that way we can plug it back into the differential equation. Now the reason for this example, why it's a lot of work, notice we have a product, so we're going to need the product rule, and we have 2x inside your sine and cosine functions. We're going to need the chain rule. So this term requires product and chain rules, and so does that. Now as a differential equation students, this shouldn't be complicated for you, but it certainly is very tedious. So let's go ahead and take our time. We're going to calculate our derivatives. Using the product rule, we'll differentiate this function first. We'll get a times sine of 2x. And when you differentiate your sine term, the chain rule gives you a factor of 2, which I'll put in front and write this as 2 times ax plus b times cosine of 2x. All right, we're going to move on now to differentiating the second term here. Again, apply the product rule, so we'll get a factor of c for the derivative of the parenthesis part. So c times cosine of 2x. And now, when we differentiate cosine, the chain rule again gives us a factor of 2, but the derivative of cosine is negative sign. So we're going to get minus 2 times cx plus d times sine of 2x. Now, I always like to simplify and clean up my derivatives before I move on to calculating higher order derivatives. And you can see here, through parentheses and all the other terms, we have sine terms and cosine terms. So let's see if we can group the sine terms together. Looks like in terms of the x that we have in front, because we expect a degree 1 part times sine or cosine, looks like we have a minus 2 cx. What else do we have? We have an a for a coefficient of a sine term, and then minus 2d. All right, notice how I'm writing the part in parentheses in the same form, a degree 1 polynomial, x, and then constants. It's going to make it a lot easier for me to keep track of the work if I order it appropriately. Now we're going to also look for the cosine terms. We want to look for anything with an x times cosine. So it looks like we have that here, 2ax. And what else do we have for our cosine terms? We have a 2b. And what else do we have? A c. All right, and that is your first derivative term. Let me just write yp prime there. And we're going to have to apply product and chain rules again to get the second derivative. So, deep breath, let's get to it. Yp double prime. We're going to again first differentiate the part in parentheses. That just comes out to negative 2c. And that's times sine of 2x. And then again, when we differentiate the sine term, the chain rule gives us a factor of 2. So plus 2 times all this stuff, negative 2cx plus a minus 2d. And then sine differentiates to cosine. And we go through this again to differentiate this term. So take your time, differentiate the part in parentheses. You'll get a factor of 2a. And that's times the second function, cosine of 2x. And we already know the derivative of cosine will be a negative. Chain rule gives me another factor of 2. So it looks like I'll write this derivative as minus 2 times 2ax plus 2b plus c, but now times sine of 2x. We're going to again simplify this, collect the terms together, writing it in the form of a degree 1 polynomial times a sine, and then similar degree 1 polynomials times cosine. So let's see if we can extract first our sine terms. We have a sine term here, the other one's over here, but we want to look for the x's first. So we have a negative 2 in front. That's going to distribute in to give us negative 4ax. All right, what other coefficients do we have from this part? We get a minus 4b. We get a minus 2c. But we also have another sine term right here. So minus another 2c, negative 2c minus 2c. We can write that as minus 4c. That all multiplies sine of 2x. We should be able to collect all the cosine terms. Let's look for the cosine terms that have an x in them. So we have that right here. Looks like we distribute that and we're going to get a minus 4cx. All right, and what are the other constants that we get? Looks like plus 2a. Looks like we get a minus 4d. And we should have another cosine term right here, plus another 2a. 2a plus 2a. Same as earlier, I'll write that as 4a. And that is multiplying your cosine of 2x term. All right, that is, again, your second derivative. And we have almost all the hard work done. We have our function term. We have our first derivative term, but notice in your differential equation, you're missing y prime. So we're not going to have to worry about plugging this back in, but we do need our simplified version for the second derivative, since that's a term in your differential equation. Now that we have yp, but more importantly, yp double prime, we're ready to plug these in and solve for the values of our four unknowns. Now you can see the expression here for yp double prime is rather long horizontally. And if I were to try to plug all this in to my differential equation, just keep going horizontally, I'm going to go off my board and you're probably going to go off your paper. So rather than write all this down horizontally and just, do more work, more writing, what we're going to do is notice we've already kind of lined the terms up. We have our sine terms, our cosine terms, and we've even ordered the parentheses with x first, followed by constants. So we have these already lined up. We're not going to write them down horizontally again. We're just going to extract the like terms and group and add them together. So we're going to plug these in, replace your y with yp. So we have yp prime plus 9 yp, and we want this to equal x times sine of 2x. Our yp term up here, we're multiplying that by 9. So let's see if we can get our like terms here. We're going to multiply this by 9, and then we add it to yp double prime right below. So what would your sine terms give? Let's look at the x's in parentheses first. This one is multiplied by 9, and we have minus 4ax. So it looks like what we get, 9ax minus 4ax, 5ax. That's going to be your sine of 2x term. What are your constants? This is multiplied by 9. Add it to here. 9b minus 4b. That's 5b. And we don't have any c or d terms in there, so we have minus 4c. And that's times sine of 2x. And we have similar terms coming from the cosines, but remember, yp, we're multiplying that by 9. So let's go ahead and see if we have any like terms. This gets multiplied by 9, so we have 9cx minus 4cx. Looks like we can write that as 5c times x. All right, we're multiplying this by 9, so 9d minus 4d, that's 5d, but we have 4a by itself. So in parentheses, we'll get 5cx plus 4a. And then remember, this was multiplied by 9d minus 4d plus 5d. And that is times cosine of 2x. Now all this stuff is the left side of that non-homogeneous ODE. The right-hand side here, this all equals x times sine of 2x. Now in class, I tend to lose a few students because this part's a little bit tricky. What are the like terms that we're going to equate on both sides? Look at your structure of terms here. You have sines and cosines, but multiplied by degree 1 polynomials. Now you have a part of that here, x sine of 2x. That's like your ax sine of 2x term, but we might expect just a number, b, times sine of 2x. We don't have just a sine term here, but I can include it with a 0 coefficient. So think of there being a term, 0 sine of 2x. And in order to equate like terms on each side, notice we are missing x cosine terms and just cosine terms. So we'll include two more 0 coefficients, 0x cosine of 2x, and then plus 0 cosine of 2x. Now we're ready to get our equations, and the like terms that we're going to equate are basically what we just wrote down. We have 4 of them. We have x times sine of 2x terms on each side. We have just sine of 2x terms. We have x times cosine of 2x terms. And the last type of terms we have on each side are just cosine terms. All right, make sure you get this, why I included those missing terms with 0 coefficients. It's going to make it really easy to equate the appropriate like terms on each side and their coefficients. So if we equate here, like terms, the coefficients of x sine of 2x terms, here we have x sine of 2x, the coefficient is 5a. And what is your coefficient of x sine of 2x here? There's a 1 in front, and we get a really simple equation. That you can solve immediately, which is nice. Looks like you get the value for a as 1 over 5. We got that easily because we took our time with calculating the derivatives and organizing everything nicely. So that way we could very quickly get to here and get that equation. All right, let's move on to now getting our coefficients for sine of 2x. These are all the parts in parentheses without any factors of x. So we have 5b minus 4c. And what's the coefficient of your sine of 2x term? Well, that's 0. All right, hopefully you're seeing how we're getting these equations. Next, we go to our x times cosine terms, and that is right here. On the left, our coefficient is 5c. And, well, notice we don't have an x cosine term, or we do, but it has a 0 coefficient. So we get 5c equals 0. That's nice because that tells me that c equals 0. And notice the equation right above, if you plug c as 0 into there, you're left with 5b equals 0. That implies that b is also 0. And again, hopefully you see the benefit of really taking your time here and making sure you order your terms appropriately. That really pays off, like we're finding here. All right, our last equation, these are just your cosine of 2x terms with no x. So we go on the left side, our coefficient would be 4a plus 5d. And on the right side, your cosine of 2x coefficient is 0. Now, we have the value of a, so you can plug that in. So if a is 1 over 5, looks like we get 4 over 5 plus 5d equals 0. You can go ahead and subtract 4 over 5 and then divide by 5. And it looks like you should get d as negative 4 over 25. Now, again, just to make sure you see how we were very quickly able to solve this, that was only because of the time we spent earlier in calculating the derivatives and, again, organizing our work. I know I keep saying that, but that's a really nice trick to apply, especially for these longer problems. All right, all we need to do now is just plug these values of a, b, c, and d back in, and we get our full solution. All right, we have our 4 values. Let's go ahead and plug them in. Half the terms are gone since we found b and c as 0. So it looks like what remains here, b is gone, but we have a times x, so it looks like yp. We get 1 over 5 x times sine of 2x. And what survives in your second part here, c is 0, but d remains, which is negative 4 over 25. And that multiplies cosine of 2x. And that is the particular solution. Good habit is to always write down your full solution, which is the complementary solution plus the particular solution. So we had our complementary solution earlier as c1 times sine of 3x plus c2 times cosine of 3x. And we add to that the particular solution, which we have here, plus 1/5 x sine of 2x minus 4 over 25 cosine of 2x. I hope you enjoyed the tips and tricks that we mentioned for organizing your work. That's very useful for the longer problems, and it's going to come in handy for even longer still problems, what you might be getting to beyond your differential equations course. Hope you enjoyed the content. If you did, support the channel, like and subscribe.